Working in our next section of Chapter 3, we're looking at the periodic trends. There's one section in here that talks about metallic character in your book. Don't worry about it. Don't read it. Don't bother even looking at the pictures. We're not going to cover it at all. Okay? Any questions, any Q and P's that have metallic character as part of that question, just go ahead and ignore that. Do the other parts that deal with valence electrons, atomic radius, and ionization energy, but don't worry about the metallic character. So in section 6 and 7, we talked about where the electrons could live. Then in section 7, we talked about where the electrons actually do live on each atom or each different element. And this is important for us because electrons are what do chemistry. The electrons are what are interacting with other atoms. It's how chemistry occurs, is a change in electrons. So we're very interested in these electrons. In particular, we are interested in the valence electrons. Okay, these are electrons that are in the outermost level, the highest energy level. So they have the highest quantum number on that atom. Okay. Also, by the electrons being in the highest energy level, they're going to be the farthest from the nucleus. So they're farthest away from the thing that's holding them on that atom. So those electrons that are furthest away can interact with other electrons. Okay, and that's why these are important to us, is because if we understand where those electrons are, where these valence electrons are, we can then discuss how they can interact with other electrons. These valence electrons do the chemistry in a chemical reaction. They're very, very important. And we have different ways of representing them. The electron configurations are one way. Another way that we have are electron dot symbols. They're also called Lewis dot symbols. So they're a more visual way of representing these electrons than the electron configuration is. These electron dot symbols use a single dot for each valence electron, and we build those electrons on the four sides of our chemical symbol. We want to put them individual until we have to pair them up. So I want to take us back to our previous lectures page, looking at our drawing that we did. Okay. The valence electrons, the outermost electrons, they're the electrons that are in the highest quantum number. Okay, so one convenient thing about our abbreviated symbol is it does the work for us, in that all of the electrons that are represented in the neon configuration are not valence electrons. The ones that we add to it, these are the valence electrons. So if we look at krypton here, it has argon, all of the base electron configuration of argon, then 4s1. So it's going to have one valence electron. Calcium is going to have two valence electrons. Arsenic here has 2 and 3, so 5 valence electrons. So does nitrogen, because it has 2 and 3. Over here, boron has 3 valence electrons. Aluminum has 3 valence electrons. Carbon has 4 valence electrons. And remember that we're getting these total numbers from our group number. Okay, the group number tells us how many valence electrons an atom has. Everything in group 1A has 1 valence electron. Everything in group 2A has 2. 3 valence electrons, 4 valence electrons, 5, 6, 7, and 8 valence electrons. So let's look at nitrogen, has 5 valence electrons. So our Lewis dot symbol, we would have our symbol for N for nitrogen, has 5 valence electrons. So 1, 2, 3, 4. Okay, we want to keep the dots by themselves until we have to double them up. We do have to double up the 5th electron there. So we have 5 dots around nitrogen. Nitrogen is in group 5A. Phosphorus, also in group 5A. So it's going to have the same dot structure. We have 1, 2, 3, 4. And it doesn't matter where we put the doubled up electron. We can put it on top like we did nitrogen. We could put it on the right side. We could put it on the bottom. It doesn't matter as long as we have 5 dots there. If we looked at another example, say aluminum is in group 3A. It has 3 valence electrons, so it gets 1, 2, 3. Fluorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. If we had, say, hydrogen, has only 1. It gets a lonely dot. And again, it wouldn't matter if we put that to the right, to the left, to the top, to the bottom, just so long as we have 1 dot on there. Let's do one more. Magnesium here is in group 2A. So we can go 1, 2. We could put these 2 dots across from each other. We could put them up and down, put them on the right and the bottom. Again, doesn't matter where we put them as long as we have 2 dots on there. The only exception to what's going on here is helium. Helium's in group 8A, okay, but helium only has 2 electrons. Those 2 electrons are in at the s orbital, so they actually do get paired up. This is the only exception. Otherwise, all of the noble gases get 8 valence electrons. So neon has 8. Argon also has 8. All right, next video, I'll talk about the 2 different trends I want you to focus on: atomic radius and ionization energy.